All right, so in this video, what we're gonna do is we're gonna look at bond energies and how that relates to the heat of the reaction. So we have an example reaction here, N2O plus oxygen goes to NO plus NO2. In this reaction through experimentation, we identified that this reaction here is an endothermic reaction. Okay, so that means it's absorbing heat as the reaction happens. So we would go ahead and express that by saying we have heat as a reactant. So as we're going from reactants to products, heat is being absorbed and going to form our products. Okay, so what we want to do is we want to look at this information and this data and answer a few things and be able to explain a few things. One, kind of identifying the relative strengths of potential energies present as reactants and products. And two, also being able to compare the relative bond strengths of all of our reactants with all of our products. And we're going to do that all by understanding this idea that it's an endothermic reaction. Okay, so let's go ahead and unpack this a little bit and see how bond energies relate to this. So we have heat as a reactant, and remember we defined heat as the transfer of kinetic energy. So that means our system, right, our reaction, is absorbing energy in the form of kinetic energy as it goes from reactants to products. Now we see it doesn't stay as kinetic energy because the total energy must remain constant. Okay, so the total energy here must be constant to the total energy here. That's the first law of thermodynamics, conservation of energy. All the energy as reactants should equal all the energy as products. Well, what we see as reactants, our total energy, we have this kinetic energy and potential energy expressed in our reaction. Well, then as we go to products, and I'm going to go ahead and put this here as our reactants. As we go to products, that kinetic energy is transformed into potential energy. And so now the total energy over here, expressed simply in our reaction here, is included in the potential energy of our products. Now the sum of these two must equal the sum of our potential energy. So what does that tell us now? Well, now we know that the potential energy of our reactants is less than the potential energy of our products. Now, how does this relate to bond energy? Okay, well, bond energy tells us how strong of an attraction we have between two atoms. So for example, up here we have our N2O, so we think about nitrogen, nitrogen, oxygen, 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 nitrogen, oxygen, nitrogen, and then surrounded by two oxygens. So now, as we look at these bonds here, we're going from reactants to products. As we go from reactants to products, we're going to have to break these bonds. And then we're going to go ahead and form these new bonds. Okay, well, breaking these bonds over here takes energy, right? We have two things that are attracted to each other, oxygen and oxygen. We pull them apart. That takes energy. We have to break those attractions. Okay, we're forming new attractions. What we're doing is we are releasing energy. Okay, so we can think about breaking as an endothermic step, releasing energy, forming bonds as an exothermic step. The relative strengths of these bonds tells us something about the potential energy of those. Okay, so over here, right, with a lower potential energy, something that has a lower potential energy, like our reactants here, okay, since it has a lower potential energy, that tells us that we have stronger attractions. Right? And we talked about this in class already, that the stronger the attractions, the stronger two things are attracted to each other, the more the potential energy decreases. So the potential energy of our reactants here, since it is less, tells us they have stronger attractions. Well, what attractions are present here in our molecules? Bonds. So that will let us know that we have stronger bonds. And that we're thinking about cumulative among all the reactants. So the sum of nitrogen-nitrogen, nitrogen-oxygen, oxygen-oxygen bonds is stronger, lower potential energy than our products here when we're thinking about, again, the sum of all of our bonds over here. Nitrogen-oxygen, nitrogen-oxygen, nitrogen-oxygen. Okay, so we have a difference in potential energy is caused by a difference in bond strength. Okay, so what we're doing here is we're starting at a lower potential energy, ending at a higher potential energy, and that's because we're starting at stronger bond strength, ending at a weaker bond strength. Okay, so higher potential energy, weaker bonds, lower potential energy, stronger bonds. Okay, so as we go from reactants to products, we are decreasing the strength of our bonds. This is why we release or absorb energy as reactions happen. Okay, we have this transfer of kinetic energy because what we're doing is we're changing the potential energy of our reactants to products. So if we have stronger bonds that we start with, ending at weaker bonds that we end up with, we got to add energy in because we're decreasing the attractions, increasing the potential energy. The opposite is true. If we start with weak bonds and we end up with strong bonds, those strong bonds have a lower potential energy, and because of that, those stronger bonds, as we form those stronger bonds, it's going to release energy in the form of heat, right? It's going to be an exothermic process. So hopefully now we see the connection between what we observe, endothermic, exothermic, and how that connects to the bond strength. Okay, and that difference in bond strength is what causes us to have an absorbance of kinetic energy in the form of heat, or if it's exothermic, a release of kinetic energy in the form of heat.